Hi everyone, my name is Tobias Schnabel and I'm really happy to talk today about our work on local factor models for large-scale inductive recommendation. This work will appear in a few weeks at Rexis 2021 and is joint work with my former intern Long Chi Yang, my manager Paul Bennett, and Susan Dumais. We started this project by thinking about how people and information items such as websites or URLs interact. And we think that it's natural for these items to form co-clusters with people. So let me be more specific. For example, we would have a group of hikers and they would interact with websites such as hiking destinations, hiking forums, hiking equipment, and so on. And then you can imagine that there's also a group of, let's say, New Yorkers that might overlap with hikers or not. And they are interested in local stores, food trucks, street fairs, real estate, and government resources in that area. And so you could think of essentially the entire item and user space being made up of such a collection of co-clusters. And the key idea here in this project was to use these information communities to improve recommendations. And we did this by including it essentially in our model architecture as an inductive bias. To give you a little bit of context of what prior work has done, well, there's been a lot of work on classic recommendation models. So there were matrix factorization-based models, and more recent, like deep learning-based models. But these models, in essence, don't really explicitly capture the structures of information communities. And we think that's holding them back from working even better in practice. And then on the other side are community detection algorithms for graphs. But these detection algorithms were designed for homogeneous graphs, so they don't really distinguish between users and items. And the second drawback is that they're not optimized for recommendations. So they are completely oblivious to our end goal of getting good recommendations. Our contribution in this work is that we present a recommendation model that detects and leverages information communities at scale. So let me jump right into the basic model architecture of our model that we call ELFM, end-to-end local factor model. And at the core of our model are affinity scores that tell us how much a user belongs to a community or how much an item belongs to a community. And these then get combined via a min operator to simulate a soft AND. So an item needs to be both part associated with an user as well as an item. So needs to be associated with a community, and the user needs also to be associated with the same community to really count towards the recommendation. And then finally, we aggregate over all communities. And the more communities, the higher the overlap, the higher the probability of an interaction. During training, we optimize the hold one out training loss, where the task is to predict a mass item from the training set. Okay, but how do we get these affinity scores? Well, these affinity scores themselves get computed via an attention layer from either users and the community embeddings, or from item embeddings and community embeddings in the right-hand case. We learn item and community embeddings explicitly and fully represent these in our model. However, we don't learn explicit embeddings, but implicitly compute the user representations on the fly by combining item embeddings of items that users have interacted with. Okay, to summarize, the architecture and our choices, we represent users and items by their affinity scores to communities, and that allows for model introspection and also interpretation. And then users are implicitly represented through items that they like, and that enables us to have a compact model, as well as to enable new users, to accommodate new users on the fly, because we can simply recompute the representations based on their interactions. Okay, so moving on to the evaluation, we had essentially two parts in our evaluation. There was an offline recommendation part and then an online user-centric study. And I'll first talk about the offline results. So for the data sets, we had 3 different data sets of various sizes, 2 public ones, and then 1 that we collected from Bing. So the Web 35 million data set we collected from Bing, where we looked at browsing sessions and all the links that got clicked repeatedly. We ended up with a really sparse data set here that had about 3.7 million users and about 500K items. And then there was also a Last.fm data set and a Movie Lens data set. Those were smaller in size and had lower sparsity levels in general. For the baselines, we compared to the classic baselines such as popularity base or user KNN. And then we also had a UCML baseline, which was essentially based on metric learning, and then all the classic matrix factorization-based baselines such as BPR, weighted regularized matrix factorization, and then deep learning-based matrix factorization, and a recent model that tried to do a local decomposition similar in spirit, but was really hard to implement and scale, and we'll talk about that a little later too. In terms of the offline results, first of all, as I said, you can see that our GLSVD baseline didn't even complete, it ran out of memory on the largest data set. So that's definitely not desirable in practice. And then for the, just for the numbers, the performance of our model is best or on par with the best baselines. So here the best numbers are in bold, and then the second best results are underlined. 3 stars mean that the results are significant at a p.01 level. Okay, so moving on to the user-centric evaluation, here we used a so-called intrusion task that we presented to Mechanical Turkers, where we had essentially 3 supposedly coherent items that are given and 1 intruder. And this has been used for word embeddings or topic modeling. And essentially we generated examples by using the top 3 URLs from a random community and then inserting 1 random URL. And so it looked, the task looked something like pick the site that is least related to the others, and then depending on what website was the intruder, we counted that as kind of correct or not correct. So what we can see from the results here, we have the precision of each method reported that was measured by essentially human labels. And we can see that our method performs essentially on par with the weighted regularized matrix factorization based clustering. But what's really important to highlight here is that our method only is able to produce a high number of non-degenerate clusters, which is indicated in parentheses, which is essentially a non-degenerate cluster is when both items and users are not empty. Okay, so, and the other thing to keep in mind, of course, is that these results only hold for item clustering. In terms of the qualitative evaluation, here's a random user, and you can see that ELFM successfully decomposed it into student loans, military, and classwork, whereas the other method wasn't able to do so. To summarize, we saw that ELFM combines the recommendation and co-clustering at scale. It offers dynamic updates of user profiles and coherent and interpretable co-clusters. In future work, we would like to use that for explanations and for the detection of information silos. Thank you.